All right, Advent of Code day 8. Here we go. Jory Pie, this is Advent of Code. It's a programming competition, and I'm starting. Day 8, handheld halting. Flight to the major airline hub reaches cruising altitude. You're interrupted. Their handheld game console won't turn on. They ask if you can take a load. Narrow the problem down to a strange infinite loop in the boot code, your puzzle input. Should be able to fix it, but you first need to be able to run the code in isolation. Boot code is represented as a text file with one input per line of text. Consists of an operation. Ops equals stirs dot map do stir. Each is an instruction. Operation. Stir dot split op arg equals stir dot split space assigned number arg equals arg dot 2I op arg. Acc increases or decreases a single global value called the accumulator. Accumulator starts at 0 equals 0. Jump index new instruction relative to itself. Index equals 0. No op does nothing. Immediately before, okay. This is an infinite loop. With this sequence of jumps, the program will run forever. The moment the program tries to run any instruction a second time, you know it will never terminate. Immediately before the program would run an instruction a second time, the value in the accumulator is 5. Okay. Scene instructions equals set.new loop do if scene instructions dot include next inst break puts accumulator op arg equals ops next instruction case op when accumulator when jump when nop does okay, so next inst plus equal 1 scene next scene arg jump next inst plus equal arg. Seven. Not the right answer. Dang it. Jump to a relative to itself. Accumulator. Oh. Next inst plus equal to 1. 1563. 30 seconds. It's killing me. That's killing me. 21 seconds. 1563. 13 seconds. 8 seconds. 1, 2, 3, 4, 5, 6, 7, 8. Poor. Part 2, you leave exactly one instruction is corrupted. somewhere in the program, either a jump is supposed to be a nop or a nop is supposed to be a jump. Program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. By changing exactly one jump or nop, you can repair the boot code. Okay. So if it's a jump, if next inst plus 1 equals ops dot count break, if break if next inst plus arg equals ops dot count. After oh, okay, that doesn't work. Let's see. Ops dot count dot times do def run ops while next inst break if next inst equals ops dot count. Next inst equals ops dot count nil. Break if next inst equals ops dot count new ops equals ops dot dupe new ops changed equals ops change op arg equals ops dot I. Next if jump new ops I equals nop arg, else jmp run new ops val equals break if val puts val break puts dupe. Yes, I did mean dupe. Ops 47 767. Cool. Bummer. Not. Felt like it did a lot better on this part too than 203rd. But oh well. All right, this is the beginning of our interpreter, I guess. So that's fun. All right, what are we doing here? Run puts part 1, run ops puts part 2 val. Oh. Part 1 part 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 if part equals 1, else accumulator. Part 1, and then here part where we run it, part 2. Cool. December 8th, 2020 solution. Let's see how we did today. Oh man, not very well. 9. I did solve part 2 fast, but not that fast. How about this leaderboard? First to finish. And these leaderboards, no one participates. Yep. Okay, cool. So let's go over this problem again and go over my code. And why is there this extra line? That's interesting. Day 8, handheld halting. Your flight to the major airline hub reaches cruising altitude without incident. While you consider checking the in-flight menu for one of those drinks that come with a little umbrella, you are interrupted by the kids sitting next to you. Their handheld game console won't turn on. They ask if you can take a look. You narrow the problem down to a strange infinite loop in the boot code, your puzzle input of the device. You should be able to fix it, but first you need to be able to run the code in isolation. In terms of the story, you narrow the problem down, so there's an infinite loop, and in part 2, after some careful analysis, you believe that one instruction is corrupted, and so we fix this kid's game device and save the flight for them. All right, so how is it actually implemented? Boot code is represented as a text file with one instruction per line. Looks like this, my input. One instruction per line. Each instruction consists of an operation, accumulate, jump, or no op, and an argument, assigned number like +4 or -20. Accumulator increases or decreases a single global value called the accumulator, or ACC, ACC, by the given value in the argument. For example, ACC +7 would increase the accumulator by 7. After an ACC instruction, the instruction immediately below it is executed next. JMP jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from the jump instruction. For example, jump +2 would skip the next instruction. Jump +1 would continue to the instruction immediately below it. Can also go backwards. NOP stands for no operation. It does nothing. So then give examples. Run your copy of the boot code immediately before any instruction is executed a second time. What value is in the accumulator? So we parse all of our operations like this. We just split on the space, and then we can call 2i on it. Luckily in Ruby, plus 35.2i returns 35. So we have our operations, and then we're just going to run it. called this function. So we have an accumulator, which is 0, next instruction, which is 0. We have a set of seen instructions, which is a set. So we're going to just loop, and we're going to break if we've seen the next instruction, because then that implies that we've found, if we've already seen the next instruction, because that implies an infinite loop. Ignore that. This is used for part 2. Next, if break if the next instruction is op_stat_count, which means we've gotten past the last instruction, so there's nothing more to execute. So we get the operation and the argument. We say that we've seen that instruction, and then if it's accumulator, we increment the accumulator, increment the instruction counter. If it's a jump, we increment the next instruction by that value, and if it's a no-op, we just move to the next instruction. And then at the end, when we break, if the part is 1, we just print out the accumulator. Then for part 2, after some careful analysis, you believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a no-op, or a no-op is supposed to be a jump. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. That's what this line up here is for. So by changing one jump or not, we can repair the boot code. And after we repair it, what is the value of the accumulator before the program, right before the program, or after it terminates? So what I do is, for every instruction in ops, so it's length times, I'm going to duplicate the array, duplicate the ops, and then I'm going to get the op at that index. If it's an accumulator, I can't change it, but otherwise, if it's a jump, I'm going to replace it with a nop, and if it's a nop, otherwise I'll replace it with a jump, and then I will run the same program, but with this part 2 argument. And now when part is 2, this is down here, if the next instruction is the length of the operation, so it's the last instruction, that means we finished. Rather, if the next instruction is something else, that means that we infinite looped and our modification didn't help. So if it actually terminated correctly, then we return the value of the accumulator, otherwise nil. And so when we run it with the part 2 on, if we get a value back, that's our answer. Yeah. And so when we run it, that's what we get. And that is Advent of Code Day 8.